Hello everyone. In this video, we will talk about how we can summarize a data set. And with summarizing, I mean, can we find the center of the data? Can we have an idea of what are the deviations we can expect from the center, and how can we use these measures to quantify whether an observation is an outlier, an extreme observation, or not. Because in the previous videos, we talked about um, outliers, high leverage points, and finding structure in the data set. But that was more on a visual basis. There we say, well, if this is the histogram, then all the data is here, and then this is an extreme observation, because it does not follow that regular pattern. Let's now try to put numbers on it, try to quantify what is the structure that I find in the data set, and when is an observation sufficiently different from the bulk of the data. So we try to do here. And we start with finding the center of the data. And probably you notice that the two most used measures for finding the center of the data are the mean and the median. The mean, very simple, is defined as the average. You sum all the observations, you divide it by the number of observations. The interesting thing about the mean is that it has a lot of nice properties. It's an expectation. It's an estimator for the expected value of a random variable. If you calculate a standard deviation, a variance, then you need this number, the mean. So you can say that if you can, it's always good to calculate the mean. It's always useful to know the mean. However, as a measure for the center, sometimes the mean can be misleading. And why is that? Because the mean is sensitive to outliers, to extreme observations. If one of the xi's is very large or very small, that will have a big influence on your mean. So especially when you have skewed data means that it looks like this. So you have one part of the data where you have lots of observations, and then the other observations are spread out over your, in this case, right tail. You can also have a skewed distribution to the other side, of course. And then these few large observations will pull the mean towards larger values, of course. So in that case, the mean is not the best measure for the center. However, if you want to calculate the variance of your skewed distribution, you still need the mean. Right? So that's why I say the mean is, apart from being the center of the data or being a measure for the center of the data, is also useful as input for other measures. Another measure for the center of the data is the median, and the median is where we say that is the middle of your data set. So if you have x1, which is smaller than x2, smaller than x3, smaller than x4, smaller than x5, for example, then this is your median. If you have 6 observations, then your median is the average of x3 and x4. Right? So it's the middle between x3 and x4. In that case, the median is always the value such that you can say, well, 50% of the data is on one side of the median and the other 50% is on the other side of the median, which makes it a good measure for the center of the data. If your mean and your median are very similar, close to each other, then you have, in most cases, you have a symmetric data set. If your mean and your median deviate from each other, that's a sign for having skewed, non-symmetric data. And then you have to be careful on what you use as a measure for the center of your data. Let me illustrate the difference between the mean and the median with a very simple example. So assume we have a data set with values 1, 2, 3, and 4. In that case, you can calculate that the mean, you sum all the observations, you divide by 4, you find that the mean is equal to 2.5. The median, we have 4 observations, so it's in between 2 and 3, it's also equal to 2.5. So in this case, the mean and the median are the same. Assume now we take a data set which has the same observations, 1, 2, 3, and 4, but now I add an extreme observation, I add 10. In this case, the mean is equal to, you add all the observations, plus now you also have this 10, you divide by 5, because you have 5 observations, you find that the mean is equal to 4. So the mean, by adding just one observation, jumps. It is now 4. It was before, it was 2.5. So that is an increase of 60%. So by adding one observation, your mean changes by 60%, increases by 60%. Let's see what happens with the median. The median is the middle of your 5 observations, which is 3. Your median is 3. So your median only goes from 2.5 to 3. It becomes a little bit larger because you add the 10. And in this case, it's an increase of 20%. So by adding an extreme observation, your mean directly jumps by 60%, whereas the effect on the median is much smaller, only 20%. And that's why we say if you have outliers, then sometimes the median is a better measure for the middle of your data than the mean, because you see here in your results that the mean is equal to 4. Here you see 4, and 4 is clearly not the center, the middle of your data. I think that in this case, it's reasonable to assume that 3 is a much better indicator for the middle of your data. We discussed the mean and the median as measures for the center of the data. And with center, we mean we try to find the middle of your data set. Let's now be a little bit more general and try to find the location of your data. And that we do with the Q quantile. And the Q quantile of a random variable x is defined in this way. And I made a separate video to discuss this Q quantile in detail. So I advise you, if you are not familiar with quantiles, maybe you are because you took a course on probability theory, then you know what a quantile is, but if not, have a look at that video. So assume that you know what a quantile is. Then we know the Q quantile by xq. And how do we use the quantiles? Well, if we have a distribution, fx, for a random variable x, and I assume, to make life easy, that my distribution function is continuous and strictly increasing. It means that my distribution function looks like this. We want to define, or we want to find the Q quantile, and Q is a value between 0 and 1, of course. It's a probability. And if this is my distribution function, my cumulative distribution function, the probabilities are on the y-axis. So assume that this here is Q. Then what is the quantile, the value that corresponds with this Q? Well, let's have a look in this definition here. We take the infimum, or the minimum, of a set. So the Q quantile is the infimum, so the smallest value, of a set, say A. What is this set A? In this set A, there are values x on the real line. Here is the real line, right? So I look for x values, and what x values are going in my set A? There are the x values such that if I apply my CDF on this x value, I should end up above Q. So I had my Q on the y-axis. I indicate the level of Q by this red line. So I'm looking for x values such that if I apply the CDF, I should end up above the red line. So for example, if I take this value here, I apply my CDF, I end up in this value, I end up below the red line, so that's not in the set A. right? So, and then I hope that you see that all these x values, because my distribution function is increasing, all these x values are in the set A. And then the smallest value of that set A, it's this value here. That's my x cube. Right? So that's how we find the quantile in case of a strictly increasing and continuous distribution function. And then remember that my distribution function is defined as the probability of being smaller than some level. So it means that if I take x cubed, then the probability that my random variable x is smaller than x cubed, so the probability that x is in, say, in this region here, that is exactly equal to q. So my q, or my quantile, x cubed, divides my data set in two parts. It says we have a probability q of being on one side, being smaller than x cubed, and we have a probability 1 minus q of being larger. And that's a way to find the location of your data. For example, sometimes you want to have the what we call the first quartile. It's x 0.25. You want to find the value x such that 25% is smaller, 75% is larger. If you take the second quartile, the 50% quantile, that's the median, because you have 50% on one side, 50% on the other side, in the middle of your data. And then we have the 75% quantile, these are your large observations, such that 75%, meaning the majority of your data is smaller than that value, and 25%, a small number, is larger. Assume that you have a data set with values x1, x2, xn, and I assume that x1 is the smallest value, then you have x2, then you have x3, and so on. And moreover, to make life easy, I assume that I have all different values. So there are no two values in my data set that are the same. Then, on the previous slide, I discussed the inverse CDF, the quantile function, and to calculate the quantile function, for example, to calculate the first quartile, you need the distribution function. You need f, the distribution function of the random variable x. The random variable x, that's the random variable that is used to simulate, or well, you assume that your data are realizations from this random variable x. I need that distribution function. And of course, if you have a data set, you have data, you have the xi values, but you have no distribution, no random variable, no distribution function. So let's see how we can build what we call an empirical distribution function. So we want to construct a distribution function based on the data that we have. However, assume that the xi values, your data set, are realizations from a random variable. Then you don't know what random variable it is. Maybe it are realizations from a normal distribution, or maybe some other distribution. You don't know that. Meaning that if you try to reconstruct your empirical CDF, it's a different CDF than the real CDF of your random variable x. Of course, you hope that they are close to each other, especially if you have lots of data, but they are different objects. One is the real distribution function, the one you don't know. The other one is the one you can calculate, but only based on the data set. So that's why we use this hat, f hat, denote is an empirical distribution function based on the data and different from the real distribution function. What we do is we say we take this indicator function I, where if I take xi, one of the observations, I check if xi is smaller than my argument x. If that's the case, this indicator function will give you back 1. In the other case, it will give you back 0. It means that with this sum, we count how many of the observations in my data set are smaller than x. I divide by n to go from the number of observations smaller than x to the probability, empirical probability of being smaller than x. And then we find that if my data points are x1, x2, and so on, and say here is xi, we have xi plus 1, then my empirical CDF f hat is of course 0 as long as x, I have my x values here, is smaller than x1, because there are no observations smaller than x1, so this will give you back 0. So you find 0 until you reach x1. There's only one observation in your data set that is smaller or equal than x1, it's x1 itself. So this summation will give you 1 divided by n. Your CDF jumps from 0 to 1 over n. If you reach x2, there's only one observation that is, there are two observations that are smaller than x2, it's x1, and it's x2 itself. So it jumps from 1 over n to 2 over n. Of course, in between x1 and x2, it's always 1 over n, right? Because if I take this x value here, there is still only one observation smaller than x value. It's x1, because x2 is larger, so it doesn't count. x1 is still smaller. And it continues like that. So you make steps, jumps, of 1 over n. Meaning that if you reach xi, your CDF is I over n, because there are exactly I observations smaller or equal than xi. If you reach xi plus 1, you have a probability I plus 1 over n. Right? This is your empirical CDF. Assume now that you want to get your empirical quantile. So you want to have your quantile with level Q, but now based on the empirical CDF. Then you see that if you take, for example, Q here, in between I over n and I plus 1 over n, your empirical quantile is equal to xi plus 1. So as long as Q is in between I over n and I plus 1 over n, your quantile is xi plus n. So if we have data, we can construct an empirical distribution function, we can get empirical quantiles. In this plot, I have two histograms, one with normally distributed random variables, the other one with log normally distributed random variables. So let's start with the normal distribution. So I take a normal distribution, mean 0, variance 1 in this case, and I simulate a data set. The blue line is the mean of the data. So that indicates where is the middle, the center of my data set, around which all observations are located. Then to get a better idea of where my data set is, I add two quantiles, the first quartile, the Q 0.25, and here the Q 0.75. It means that in between the two red lines, I have 50% of my data. So I have the mean in the middle, and the say the majority of the data is in between the red lines. In this case, we have a symmetric distribution, so you see that the distance from going from the mean to Q 0.25 or from the mean to 0.75, it's roughly the same. Right? It's symmetric data, so we have deviations around the mean, but the deviations in one direction are more or less the same than the deviations you can expect in the other direction. If we move to the log normal distribution, this is different. Again, the blue line indicates the mean, the center of the data, and the red lines are the two quartiles, the Q 0.25, Q 0.75. So again, 50% is in between the red lines. And in this case, you see that the mean is much closer to the Q 0.75 because the mean is sensitive to these outliers. So in this case, you see that the mean is not a very good indicator for really the middle of your data, because most of the data is in between the red lines, and the mean is pushed towards the Q 0.75, pushed towards the rather large values. Inspired by the previous plots with the histograms and the center and the quartiles, we want to measure the spread of the data. So how much, to what degree, is the data spread out? So the easiest way to get the spread is to calculate the range. Just say what is the largest value, what's the smallest value, and everything that happens in the data set happens in between the max and the min. The drawback of the range is that, of course, it's very much affected by extreme observations. You only need one very large observation to get a very large range. Even if most of the data is very close to each other, one large observation will directly give you a very large range. Another way is to use the standard deviation, and similar to the mean, the standard deviation is the most used measure for the spread of your data set. So what we do with the standard deviation, we start from the mean, the center of the data, and then for each observation, we are going to measure what is the deviation of my observation xi from the mean. And I add all these deviations and I average. I measure, in this case, the distance from an observation towards the mean using a L2 norm. I take the squared difference. In the formula, you see that I assume some kind of symmetry because I take the mean and then I say, well, if xi is here or in case it's here, as long as the difference is the same, I add the same number in my summation here. So I do not care whether xi is larger than the mean or it's smaller than the mean. What I care about is that it deviates. So the standard deviation, very good measure for the spread, but especially for symmetric data. Another way to measure the spread of the data is using the IQR, the interquartile range, and that's basically what I had on the previous slide. It's the Q3 minus Q1. In between, you have 50% of your data. So you say, well, how wide is the range that I need to get 50% of my data? The good thing about the interquartile range is that it is much more useful, intuitive for non-symmetric data, for skewed data, as we saw on the previous slide. Another less common measure for the spread of the data is the mean average deviation, which takes the same ID than the standard deviation. I measure deviations from my mean in a symmetric way, but instead of using a squared difference, I use here absolute values. And one reason to use absolute values compared to a squared difference is that it handles outliers a little bit better than the standard deviation. But again, it assumes some kind of symmetry in your data because you do not distinguish between values that are larger than the mean, values that are smaller than the mean. Let me say a few more words about the standard deviation and also the mean. We have this say rule of thumb that says, well, if I have a data set, I calculate the mean x bar, I calculate the standard deviation, then most of my data is in the interval mean minus 2 times the standard deviation, x mean plus 2 times the standard deviation. So we say that most observations lie within 2 standard deviations of the mean. In mathematical terms, we can say, well, if I have a random variable x and if I simulate realization from x, I get the mean x bar, but in probability terms, I have a random variable x, then what I want is that the probability of x, the realization of x, being within this interval, expectation x minus 2 sigma, expectation x plus 2 sigma, that probability should be large. Of course, there are distributions x for which this does not hold. So why do we still use this rule of thumb? Well, the reason is simple, as in many cases, it is because this holds for a normal distribution. And many of the measures and quantities and rule of thumb that we use, they come from a normal distribution. We use the mean and the standard deviation because they are the parameters that go into a normal distribution. We use correlations because correlations are the quantities that we need to connect two normal distributions. And the same for this rule of thumb. So let me show you why we think that this is a good idea, at least from a normal distribution. So I want to calculate the probability that x is within 2 standard deviations of the mean. So mu is the mean of my normal distribution, sigma is the standard deviation. So I want to calculate this probability. I'm going to rewrite this probability a bit. I first take the probability that x is smaller than mu plus 2 sigma. So now I have the probability that x is smaller than mu plus 2 sigma. I want to be in between this bound and this bound, so I have to subtract the probability that x is smaller than mu minus 2 sigma, because then I have the probability of being in between. Now I can calculate this as x minus mu divided by sigma is smaller than 2, minus the probability x minus mu divided by sigma smaller than minus 2. And if x is a normal distribution, mu is the mean, sigma is the standard deviation, then this has the same distribution as a what we call a standard normal distribution. A standard normal distribution is a distribution with mean 0 and variance 1. And the distribution function of a standard normal distribution is denoted by phi. So that's why I can write this as the distribution function of a normal distribution with mean 0 and variance 1, evaluated in 2, minus the distribution function of a standard normal distribution, evaluated in minus 2. And very often you have tables with distribution function of a normal distribution with mean 0, variance 1. So now we want to calculate a probability for a normal distribution with a given mean mu, a given standard deviation sigma. I don't know what is mu and sigma, so I cannot calculate, for example, this thing. Is the distribution function of a distribution function with a mean and a sigma I don't know. But I can rewrite this, and now I find this expression, and this I can calculate. Even when I don't know mu and sigma, somehow they disappeared in my equation, and now I can calculate it, and then you find that this is roughly equal to 95%. And then indeed we can say, according to the rule of thumb, within 2 standard deviations of the mean, I have 95% of my data, I have the majority of my data.